Hey, so I'm going to talk to you about phenotyping, but from a probabilistic perspective. So you've seen all this nice, well-defined rules and sets of, steps to identify phenotypes. So this is going to do something completely different. So hopefully it's not too much of a shock. So for electronic phenotyping, like we discussed, the main purpose is to identify a set of patients for observational research, clinical trial eligibility, and quality metrics and other things. Or, for a decision support system, or who's based on, similarity on identifying people for a clinical decision. Who's progressing along the same paths. So the main problems with this and the way that it's been done, you kind of need a gold standard. And this gold standard, as most people know, is expensive and hard to generate because you'll have to hire a bunch of clinicians and then have them decide, if the patients really have whatever phenotype you're defining, and then they have to agree within themselves. So that's hard and expensive. And sometimes, the majority of the time, it's getting better, but there's poor portability across sites. Basically, you and your site, you have ICD-9 codes, you define a phenotype using ICD-9 codes, then you go to your collaborator site, and they have SNOMED codes. Oh, well, you have to redefine your phenotype with SNOMED codes. Or, they're in a different country, so they don't use RX norm, they use a different drug system. So you see where this is going, that, porting those definitions, depending on the context, or depending on where, it's actually tricky. So the way that I look at phenotype, and this is for the previous work. So you have, in one dimension, the features used, where you go from list of ICD-9 codes to all features, meaning using everything you have from the patient. You have a way of defining them, where you can either start with a base query, or you do inclusion and exclusion rules. So this is getting more complicated, and then you could do a regression model, or you can do generative models and whatever fancy buzzwords, new stuff people want to try. And you have an option of either handling time or not. So you can either ignore time by collapsing your features, or you can be time aware. Again, this is coming from a machine learning perspective. So if you notice dimensions, the way they interpret the dimensions, it's a little bit different than, you can't just have a phenotype in Atlas by just completely ignoring time. That would probably not be a very good idea. So, the classical approaches, so you have the rule base. This is the most popular one, and the traditional way, you have expert consensus definitions, and you have places like PKB where you can actually go and look at certain phenotypes, and they've been validated and designed by major institutions. They agree on them, and they post this recipe, which sometimes is a Word document, sometimes it's a text file. Some of them are even Excel files with a bunch of rules. Or you have the next best thing, which is actually a huge improvement when you have them already implemented in Atlas. So you can go to Atlas, and actually you can go and pick up the phenotype from there, and just copy paste it to your site, which is awesome. But the part that I'm talking about, it's with the probabilistic side. So this is a newer trend. It's getting a little bit more popular. There's other groups doing this. And there's packages like APHRODITE, which is built on the OMUP CDM. So that's what I'm going to talk about today. And there's another sort of way of doing this with anchor learning, which is also built into APHRODITE. So that functionality, if you were aware of anchor learning for phenotyping, it's also baked into APHRODITE. So you can use it on the OMUP CDM if you have your data on it.
Excuse me, did you say APHRODITE is a package?
Yes, it's an R package.
Oh, R package. Okay, so it's not great.
Yeah, it's not a standalone. It's standalone, but it's an R package available.
And how about Anchor?
Oh, Anchors is there's two versions of it. There's the original version that doesn't use the CDM, and I built in the functionality into APHRODITE to do the anchor and learn process.
So does APHRODITE use CDM?
Yes.
Okay, so it's not a standalone R package that you can use on, say, any
Any data? No. You have to have data on the CDM underneath. Yeah. So, and I'll talk about that a little bit more in detail. So for the probabilistic phenotyping, at least for APHRODITE, the core idea is to learn from a set of label examples. So this is supervised learning. And, the advantages of this is that, you can do automated feature selection. You can reduce the number of training samples by having, a very good set of, examples. And, here you can consider the probability of a phenotype as a continuous trait. And that's exactly what Chris was talking about earlier, that you have this little plot where your probability of somebody belonging to that phenotype or that cohort can change over time. It's not just yes, no. It can go anywhere from 0 to 100%. So here with APHRODITE, we aim to create large training sets for cheap, meaning that you won't have to, if you want to validate them, yes, you will need to, at least until now, you'll still need somebody to look at them. But, we've shown and we validated this in specific phenotypes that it's not that expensive. So, for cheap in the sense that, you'll have a large training set that kind of sort of has phenotype in the sense that, it's tagged in a certain way. And I'll give more details on that. So basically, this it's built on top of the idea of learning using imperfectly labeled data, and this is achieved, or this imperfectly labeled data comes when you have a heuristic, like a labeling function, that has high precision. It doesn't matter if it has low recall, and this heuristic function can be anything from, okay, if I want people with myocardial infarction, then I'll just find people with the ICD-9 for myocardial infarction or ICD-10. Or, if you have something that doesn't have a code, you can actually look into, if your CDM has the node NLP tables or you have all your clinical narratives annotated, you can actually use those features from that space to define your phenotypes via APHRODITE. And based on this, so now you have an imperfectly labeled function, so you'll be able to create large amounts of training data in the sense that, okay, you have a function and then you set it loose on all the data you're able to look at in your CDM or whatever subset of data that you want to look into it. And then you train a classifier using this imperfectly labeled data, and you can evaluate performance if you already have, some sort of gold standard.
So what is your negative samples?
What do you mean?
What is your negative samples? Because I can see you only have positive samples.
Well, the negatives is everybody that doesn't have that.
Okay, so it's more like a positive and unlabeled sample than you.
Yes, yeah. Yeah, so if your labeling heuristic is everybody with a code from MI, your negatives will be people with no codes for MI. So does it work? And this is what I was mentioning. So we evaluated it. When I was at Stanford, we did it for diabetes mellitus, and we actually went through, so we built the phenotype using the code. Then we made a prediction on the remaining set of patients that we had at Stanford. And then it gave us some predictions. We looked at the top couple hundred of the most confident predictions, and then have a clinician say, a set of 3 clinicians, they had two votes agree on it, and they evaluated them and said, oh yeah, this person should have this. So we did it for diabetes mellitus, but 91% sensitivity and pretty good PPV. We did it for myocardial infarction as well.
I'm so sorry, I missed something. So when you created this matrix, did you extract that from the confusion matrix, or did you use physicians?
The confusion matrix. We built the confusion matrix with the physicians' data.
Oh, with the, okay.
Yeah.
So with the physicians' data.
Yes.
Okay,
So
not
basic.
Not from the model.
No. Yeah, this is with the physicians' data.
Okay.
Yeah. So basically, we set the model off. We made 200 predictions, and then out of those 200, we set people, label them as true or not, and then we fit it in. Yeah. Okay. So yeah, this is based on the chart review. So we were pretty good with diabetes. We were pretty good with MI. FH is a little bit not that great in terms of PPV, and celiac is even worse than that. So there's certain types of conditions that And you can extrapolate from this that, for some conditions might not be that great.
I may miss that. So do you use the entire database to develop this model, or you use, like the prediction model, you use a portion of the data set for training and the rest of them for validation?
Yeah, so basically you specify in APHRODITE how many cases you want to use. So you tell it I want to use 1,000 cases that will be fetched by the labeling heuristic, and it will build a model on that, and then you test on whatever other cohort you want to test, so you can test on the rest. Yeah, or you can do it in your whole database if you want. That will be expensive, but yes.
So you specify how many cases and
Yes.
how many cases you want to use.
Mm-hmm.
Did you look into why the last one, the performance of the last one was
OHDSI, I don't have the specific. This is somebody else in the lab this study, so I was just piggybacking on their work and just put it in here. So I don't have the specifics on that. So first of all, okay. So now that I tell you what is the point of this and how it's kind of done, so this it's available for the CDM in a package, and basically, if you're a programmer, the initial version of this, you basically had to go through 5 different functions, literally 5 function calls in R, and you can already have a built model and a heuristic. So I'll talk about it. So this is the architecture. Basically, each one is an isolated kind of function call. Again, I'm not going to bog down into too much of the busy work, but just mentioning that, so you're labeling heuristic. So basically, this is when you generate your keywords. So here for MI, APHRODITE, you put MI on APHRODITE, it will go to the vocabulary and find all the synonyms and related terms. So it will do a concept expansion just so you can get more people, or you can just say, I don't want any of that stuff and just use, MI, the ICD-9 for it. Because usually you get a lot more people that are scattered around depending on how your data is. Then, APHRODITE by itself, it will go find cases and controls, meaning that it will find all the patients that satisfy your label or heuristic or whatever N of patients that you want. And it will find the equivalent N of patients that don't have that as your controls. All that stuff is automatic. It will then extract all the patient data. So you can go, APHRODITE will go in and find, all the observations, conditions, drug exposures, measurements, node NLP stuff, everything that you want, every domain that you want to use. There's flags in APHRODITE to select. Oh, I want to use all this as features, and it will do it on its own. If you notice, I'm crossing off something, and this is, for example, for MI. So let's say it's an observation, or you find it in observations. So when you're learning the model and you're learning it on a code, so all the patients that you have with the code of MI, well, they've been chosen like that, right? So when you build a machine learning model, it's going to be, not ideally, but most of the cases, it will find that as the top feature, right? Because it's the thing that all the patients have in common. So it will not be very valuable to learn a model with that constraint, right? Because then you'll just basically learn a model how to find people with the MI code, which will be not very useful. So the reason we blocked this feature is that we want to learn all the other features that are related in those patients, but the MI code. Why? Because we want to apply this model later to be able to find, the people that have all the other similar features that could have MI, but they just didn't have the code. So that's where the magic happens, and where you can use this later on, to enhance cohorts that you rigidly define, and I'll talk about that in a bit. So then, once the features are extracted, it makes a matrix, huge matrix, and this matrix is represented by, all the stuff that you can find in node NLP, table or conditions, prescriptions, labs. All this stuff is featureized, collapsed automatically by APHRODITE, so you guys don't have to worry about any of that. You can tell it how to normalize. There's a few settings for how to normalize, either counts, normalized counts, or any other. There's a few other configuration options, but all this work is done for you. So you just have to basically run the function, and it will just build a model. So you can pick from random forest, logistic regression, SVMs, whatever models that are available in the carrot package in R. So you can try any of those for this. And all of this, like I said, is automatic. And then it will tell you performance based on, whatever. It does like a 75-25% split. And it's just an internal validation performance, just the metrics of the classifier. Again, this is, just the model building. You haven't predicted or done anything with it. It just build the model. But this gives you an impression if you built a pretty a so-so model in the sense that it could actually differentiate the patients that you already know. So that's all that stuff you're given out of. So here, what is the point of this? So when you have an imperfectly labeled set, I mean, those are very easy to generate. I can just say MI or use the code for MI and treat that as a true gold standard to build a model. But obviously that definition is not as precise as a phi-kV definition, right? But for me to type in MI and APHRODITE took me 1 second, and it took 2 hours or whatever amount of time to build a model. But if you define the MI, myocardial infarction phenotype, in a way like phi-kV, that takes weeks, months. So there's where the trade-off is, right? So here in practicality for us, for our MI phenotype, I mean, we can achieve, and this is again with the clinician validated data, accuracy of 90%, PPV of 91, in a process that takes 2 hours, right? Not counting the chart review. But yeah, obviously the phenotype for MI is a lot more precise because it's been defined over time and everything. So that has, a 0.98 accuracy. So, it's an 8% increase, but, that took 1,900 man hours to build.
How many did you use? How many records did the physicians review?
Three clinicians, they review 200 charts,
200. And then
patients.
did they all review the same ones? Or, like all three review the same ones?
Yes, yeah. So they all review the same, and then whoever had a score of 2,
Okay, that's good.
so we wouldn't have ties, yeah.
Yeah.
Yeah, so, so you're comparing, 8% increase in performance in something that took 1,900 man hours and a bunch of disagreements between a group of people, I guess, and versus something that in 2 hours you can put together, right? So this is where the power of doing it with a machine learning model is that, with the noisy labels, you can get good enough performance, obviously not as great, but still close enough. So the live demo, since we had awesome internet issues, I decided to not risk it. So I basically copied some screenshots of how the software will look. So it's an R package, you can install it. Actually, you can't install it on the AWS instance. I tried. Some package doesn't want to install because some low-level dependency doesn't work. So sorry, but you can go and try it at home. So I mentioned to you all the steps. And I started seeing as more steps pop up, people were thinking, man, this is kind of looking very complicated now. Well, for APHRODITE now, there's a Shiny app on top of it. So you basically set up all your settings where you put, what concept do you want. So there you have a little field for, here I'm looking for myocardial infarction, but it's a little bit garbled up. And then all my database setup, what model do I want to use, the lasso, how many cases, how many controls, what kind of feature spaces that I want to look for the label heuristic, and what kind of feature spaces do I want to actually use as features for my model. So all this stuff you do in the Shiny app, yeah?
Just some questions related to features.
Mm-hmm.
So for condition is pretty simple. You just extract condition binary. It's like binary conditions, right?
Uh-huh.
1, 0, 2.
Well, you can specify, you can do counts. Yeah, because the time constant, I mean, the time gets collapsed. So if somebody had 150 counts, 150 instances of MI, right, it will be counted as 150 and then normalized. But the time factor gets collapsed.
I see. So it's collapsed.
Yes.
So how about measurement?
The labs get binned. So if you have the above range, below range, it will create a little bin for each one, and then you do counts in those as well.
I see.
And if you have the numeric value, then it kind of does a min-max kind of thing and then do the same procedure. So you get bins rather than just having yes, no.
But how about, I'm sorry.
Sorry?
How about jobs? Because jobs we will have different ingredients, the dosage, right?
Yes, no, for the dosage is, that's a very good point, and yeah, the dosage is not taken into consideration. It's considered at the ingredient level, yes, but anything above that, it's not, yeah.
So you mentioned case and control.
Mm-hmm.
So, but when you, okay, so why would you have a case and control for building this phenotype? Are you building the case and control because you want to use the phenotype for analysis, or?
Well, I want to build a machine learning model that knows what it's the condition and what it's not,
I
yes.
see, so it's just for the one.
Yes, because otherwise, it will be overfitted if you only feed it positives, right?
Okay, got it. That's
Yeah.
fine.
So yeah, so you have this, you pick all your features, nice. Then you go over there, you refine your labeling heuristic. So here you get all the related concepts to myocardial infarction. You can pick some, you can add some. Again, you can pick, and then it will spit out a set of a couple hundred lines of code with all the R code needed to build a phenotype for whatever keyword you put in, whatever labeling heuristic you define, with all the settings you define. So now, this is a lot easier, right? You don't have to edit this file. It will just come out. You copy paste it to your R, done. I mean, well, you have to run it. But then you'll be good to go. Yes?
Do you also include a list of the most significant features?
Yes. So one of the outputs when this runs, it will output a bunch of files. It will output your AUC, your ROC plot, and it will output you the top end features. That's one of the settings as well. Yeah.
Can you trace it back to find out what is going to be the most likely phenotype? So if you have type 2 diabetes, it will be diagnosis for diabetes, A1C, or some other characteristics that machine can learn from it, like based in artificial intelligence.
Well, yes, ideally, and that's the case for most phenotypes, or that we define correctly. So the top features will usually surface up to be, the.
But that will be like just patients. I'm talking about for a machine to come up and say, here's my phenotype. The definition that will say the most optimal phenotype.
Oh, will this tell you a definition? No. That's a good question, but no. I mean, I'm pretty sure there could be a way, right, of looking at the top features and trying to mess with that. But yeah, no. This will only tell you what was the most predictive variables that you were using.
But I feel like that's good output to help you guide if you did want to do.
Yes. And you can see if it's, getting biased by something totally random or not, right? If you see the measurements for, anything related to heart, or versus having the top feature being something related to the foot or something, then it's like, I don't know. But also when you're using the node and LP input here, and something comes out as a feature, that's where we found, at least for the case of FH, that, there's stuff related to diet that comes up. So there are interesting things that, a clinician, I mean, they make sense for a clinician, but, you wouldn't expect them to be one of the predictive features. So it's also good to explore. And obviously, okay, so the labeling heuristic might sound limited, right? So you can just, okay, well, award myocardial infarction, it's a little bit limited, but since you guys know already how to make atlas cohorts, learn today, where you can actually build models using from the atlas cohorts. Uh-huh.
So, I'm sorry, I'm just going to summarize this here to see whether I have a high level understanding. So when we defined or said that we wanted to look at for people with MI, say for example, if we're looking at it from the perspective of support vector machine, then that would be your yes, no, right?
Uh-huh.
Case control. And then what would happen is that it will look for features of any characteristics associated with the patient that are salient to that yes, no characteristic.
Yes.
Right? And that's what you're looking to see, well, okay, based on this phenotype that we've defined, say that we'll use as a classifier, that these features actually matter.
Yes. So once you have the model built and then you feed it new patients, it will actually, you try to box those patients based on the set of features that came out relevant.
Based, okay.
Yes.
Okay, so got it. Okay, so just want to know.
Uh-huh.
And when you are looking at measurements, for example, if they're ordinal, more than one,
Yes.
how, what would you report as your threshold? Like,
Oh, well, so yes, yeah, that's a good question. So when you have the above, below, and those are easy because, they're discrete labels. When you have, numbers from whatever range, what this does is that it finds the minimum and the maximum and separates it in 5 bins by default, and then it will return you the bin values that it used to pick.
that's numeric. But
Yes.
we are breaking them into the ranges. What if you're dealing with ordinal values, which are categorical and more than one?
Okay, so those are just used as counts. So if you have yes, it will use, lab concept ID, then yes, and then no. So it will separate them. So if you have yes, no, maybe, or yes, no, unknown, then you'll have one feature for yes, and that will be counted, as many times as it appears. Yeah. Yeah, so that was the trickiest part to get this right with labs. So, but also, you can build a model. I mean, so obviously, the labeling heuristic as one code or a set of codes might be a little bit not as restrictive as you like. So you can also use Atlas. So you define your cohort in Atlas, and then you have a very rigid set of rules, right? So what would you get with APHRODITE for this? So then you can build a model that, will find all the related features for those patients. And you can then run it again against your data to find who else should have belonged to that cohort, because there are other features where, match to whatever the model has as the top features, right? So it will allow you to find patients that you can then feed back into your cohort that, were not picked out by the rigid rules. So that's what you can get extra, which, might be great, might be bad. But that's, a matter of evaluation. So you can use APHRODITE with Atlas. So you define your cohort in Atlas. You can have 400 rules. You can have all the time shifts that you want. And based on that set of patients, you can actually feed it to APHRODITE to use a machine learning model to be able to then identify patients like those that were not necessarily found by the cohort because they miss, one of the inclusion criteria or something minimal, right?
So when you define the cohort through Atlas,
Mm-hmm.
basically that cohort becomes your data.
Yes, exactly.
Or the gold standard.
Uh-huh.
Um,
Your
and
positive, so your cases, yes.
Then, so those become your cases, and then the controls will be everybody else.
Yeah, so it will pick everybody else, or you can feed it a set of controls that you picked.
Oh.
So you can also do a controls cohort in Atlas and then feed that in.
Cohort of not this.
Yeah.
Exactly.
Not that.
Yeah.
Yeah, or if you have a specific set, like for example, if you're looking at only people with like blood transfusions, then you just feed that part in.
Yeah.
Yeah.
Did you test your model across different data sets to see if one will be 95%, another?
Yes, so we've done some studies, they're still not published, but we built the model at Stanford and then tested it in a unspecified data set, and we got within between 5 and 10% performance shift, which, it's considerable if you're already in the 60s, but if you're in the 80-90% accuracy or, PPV, then it's not that bad. So we've done that for FH at least. And MI and type 2 diabetes work fine. But again, we can try it for probably celiac will be one of those that just completely craps out.
How long
So,
will it run?
what?
How long, performance-wise, how long will it run?
You mean time?
Yes.
It depends on how many patients you pick. So with a couple thousand, it can take 10 minutes. If you're not using the node-NLP, if you're using the node-NLP table, then it takes a couple hours. But I try to do, and I'll talk about trying to do it with large number of patients in the next slide. You can also use, instead of just having a label heuristic, you can use a concept set that comes from Atlas. So again, this is plugging into Atlas concept sets, and you can use that as your label heuristic. Reuse it. Why have to specify it again? So I thought we were going to have numbers for the outcome cohorts for the paper, but apparently SimPuff doesn't have any fake real data. So anyways, so I ran the Atlas cohorts that were created for this class, the Stanford data. So we found, X amount of patients for all the outcome cohorts. So then, like I told you, we could use APHRODITE on this cohort to build a model and see if we can find other people that could have gone in there. So we built the APHRODITE models. Again, this is a lot of information, but most of their PPVs were, anywhere between 88 and 96%. Again, using 75% training data and 25% testing data. And so on the so this numbers, except for the ROC curve, ROC number or AUC, it's for the on-scene testing set. So it performs pretty okay. We can get 90% of the patients that we already know belong to that cohort, right? So it's pretty decent. So what happens if we can find new patients to this? So okay, fine. Yes, I try to make the predictions in 1 million patients remaining. Not ideal. I crashed my server 3 times. That's probably because of the server's limitations, or I don't want to maybe admit bad programming. I don't know yet. And then I was like, okay, fine. I'll go for 10% of that. So I tried it on 100,000, non-overlapping patients, meaning that they were in none of those other 5 cohorts. And then we did for venous botulism. If you notice, I'm not a clinician. I butcher all this stuff always. We did find, 717 patients with a probability higher than 95%. And again, this is where it gets to the thresholding, right? Should I pick everybody that has 99%? Should I pick everybody that has 95, 80? Again, this is where you're still a little bit iffy on this. But, I assume 95, it's a nice common number on most papers. We could still complement the lower GI blip cohort by, 300 patients, 985 pages. And again, these are not validated, but it's just what the model has said that, it's 95 or higher % probable of being in that cohort. That was not found using Atlas.
How long it takes for you to run this?
With the 100,000 patients, it took 9.5 hours per cohort. Because I'm using all the node NLP features, which is basically everything that they had on their clinical notes was annotated using the OHDSI vocabulary and then was treated as one feature. So these things have almost, some of them have 500,000 features.
So this, actually the data is unstructured or?
No, it's both.
It's both?
Yeah, so it's an EHR, it stands for EHR, and it has, codes, labs, procedures, and then notes, everything on the notes.
So the notes, so the features on the notes.
Yeah, if you turn that off, it runs 95% faster. Huh?
What kind of server? Does it crash your server?
It's a machine with like 1.5 terabytes of RAM and a couple hundred cores. Yeah, it's a pretty ridiculous machine, but still, having more than 500,000 features just boggles everything down.
So are we going to have access to this presentation as well?
Yeah, it's on the share folder. Yeah.
How much, you said this, if you remove the notes, how much worse is
The performance, when you remove notes, it's usually anywhere between 10 and 15% drop. So, it's not critical, but if you want something, very, very good, then adding it helps a lot. Yeah.
And have you looked at the code performance? Did you look at the reasons why you, for ceiling, for example, were some important features missing? Was it because of the missing data?
It's usually because, like you mentioned, that there's features missing. So a lot of the stuff on the node NLP table made it to the top 30 features. So when you remove them, those features are going to bring your performance down. Yeah. But funny enough, none of them made it to the top 5, but they were all between the top 30. So removing those, chips off some percentage of performance on this. So. Moral of that story is have your notes annotated and put on the node NLP table. You had a question?
Yeah, so are we saying in the end that we're really only seeing about 1% of, or 0.7% of what we could have got in terms of BTA or venous thromboembolism? So So if you've only found 717 patients
Mm-hmm.
that could have had a VTE but didn't, is that what you said?
Yes, yeah, exactly.
1,000. So it's really a small number.
It's a small number, yes.
So you might say, well, that's okay as long as that's evenly distributed between the exposed and
Yes,
the two exposure groups, so that you haven't got a misclassification group.
that is true.
So that it's nice. What you've done to find your cohort is quite good.
Okay. Yeah, and you know, we use this a lot when we have something that you only have 100 cases, right? So if you want to build a predictive model in 100 cases, it's hard. So you want to get as many people there that, you know, makes sense to do that, right? So, but yeah, for something that has this little number of patients, then you might be okay without them. But if you really want to push and get as much data as you can from your data set, then this is a way of doing that. Yeah.
But is 95% indicates that you found only 95% of all available GI bleeds, or you have 5% of erroneous patients?
No, this is that's 95% is that those 717 patients are 95% probable of being in that cohort.
Oh, okay.
Yes. Or higher, yeah, exactly. And this is out of, 100,000, so you multiply it by 10 or whatever rate, and then that, this is on 100,000 patients. So if you run it on 1 million, you're probably going to get 7,000 patients, and that will probably improve your, if you want to include them on a model, that will make a difference, yeah.
On registering cases, then that would close a confidence interval.
Yes, exactly.
Question.
Uh-huh.
So on the unstructured data, so the idea is that all this is running on ODM, CDM data, right? So that means that unstructured data would have to be moved into this format.
If you want, this could run without it.
Oh, without it? What do you mean it could run?
So this could run without the node NLP unstructured data in it. So, but because it will only use condition, procedures, and all the other tables you have available.
In ODCN?
Yes, yeah.
But then, without it. But if you wanted to include unstructured data,
Uh-huh.
then you'd have to...
You have to annotate it and put it on the node NLP table.
That's another table in this again?
Yes, it's a standard table where you use an annotator that will find, MI, and then it will be put in there.
Okay, so but I would have to move into to that table.
Yes, yeah.
But then, okay, all right. So as long as I don't have to move it to the CDM format.
Yes.
You're basically describing a process of taking unstructured data and give it some structure,
Some structure
in the nodes NLP table.
Yes, exactly.
Yeah, okay.
And, at least for Stanford, we have 20 million nodes.
I apologize, everyone. I didn't call out that table
Oh,
because it's not something that rule-based would use, but
well, you should. That's
I should,
that's
yeah.
going to be my suggestion for Atlas.
there you go. Yeah, absolutely.
Atlas can't put it in a node right now.
Yeah, no, they can't. Yeah, so this does, but you can turn it off. So because that will kill off your performance, though, because that table for Stanford it's 7 billion rows, so it's
7 billion?
yes for 20 million nodes. That's a lot. So going through that, I have it indexed, charted, cluster indices, and it will still take a bit. Anyways, so this is where I'll lead off later to Joel's presentation. So how do we know these guys are right? That's still one of the issues, right? So they have a high probability. We know that building models with this framework is pretty okay, but not great always. So those 313 patients, are they good or not, right? So the model says so, but what will a clinician say, right? So that's where this kind of leaves it up to more review, and it will basically be cohort specific.
I have a question.
Uh-huh.
So, can you go back to the previous slide? So, can we interpret the people that were identified as 17 patients with venous thromboembolism, who were not identified by the rule-based phenotyping, but is identified by the probabilistic phenotyping?
Mm-hmm.
Is that an indicator of miscoding in the administrative database?
In some instances, it could, yes. That they were just missing, whatever code was in that phenotype.
So if you have a use case of identifying people in your data set that had the condition but were not coded,
Mm-hmm.
Can Aphrodite be a potential
Yes.
application?
Yeah, that's exactly one of the best applications that, you can build your atlas cohort, find your patients, and then build a model on top of that to identify the deltas there. Yeah.
And it may actually find false positives from the rules.
Exactly,
Because
too.
the model is like saying like, the rule said yes, but all this other data around it says I say no.
Yes.
So it could actually identify false positives.
Yeah, so you can also, separate the patients that you think you're iffy on, and then train on everything else, and then feed those back in, and you can get probabilities of, if they're true or not. So you can use, the model in many different ways to actually filter out or add in patients. Yeah.
The reason I brought that up is because in addition to the research use case, there are other decision support use cases. Operational use cases. So as somebody who's in the payment side of the industry, there's a concept called risk adjustment,
Okay.
where people who have multiple comorbid conditions get a higher reimbursement
Mm-hmm.
versus, or highest payment versus those who don't. And this is a fantastic tool for identifying the people
Yeah.
who truly are sick but are not coded to be sick.
Yeah, you're right. Exactly. That's a good use case. I might steal it from you.
That's a fantastic use case.
He doesn't say so.
So, the unsolved question says, okay, so we have this pipeline, it does all this stuff. The model comes out as a binary object. I can send it to you via email. Do we share the model? Or should I just share, my config file or the file that I executed against my CDM? How do we share this? So we should put it on a GitHub or emails or Dropbox, whatever. Well, that's trying to be solved. We're trying to build a phenotype library with John Duke and Georgia Tech, so that will be up at some point. And the biggest question here, how do we know if those patients are correct, right? And that's the hardest one. You'll have those 313, 717, whatever patients. Are you going to have a clinician sit down and look at all of them? Right? But, with the statistics and all this stuff, you can be somewhat confident, right?
You mentioned about John Duke's work
Mhm.
with phenotype libraries.
Yes.
So can you come back to the slide before? What aspect of that was the phenotype library? I guess I don't understand what a phenotype library is.
So basically, a phenotype library will be like, like Atlas has all this list of cohorts, right? So we want something that has all the list of phenotypes like that. So, and then phenotypes, but they could be, an Atlas cohort or they could be a machine learning model. So Aphrodite spits out a binary file that if it's a regression, it has all the coefficients to do the same thing somewhere else. Yes, so a phenotype library will be a place to put all those things for people to go and look at them, right? Because if I build a model,
They can be independently verified and tested
Yes.
and see how you could. It's just a library as in just a collection of different modes of phenotyping. You could have one for autism and one for diabetes, one for this. It's just a library thing, and it's just right now what's missing from the Odyssey environment is sort of a central place. If you want to study diabetes, like we don't have the diabetes phenotype algorithm that you should use.
I see.
It's kind of like up to you to decide how you want to define it for yourself.
Yeah.
If we had a more of a standardized library, then people can start doing more consistent research on the.
yes, and you can save yourself, a lot of time. So if I train something on 100,000 people and you only have 100 people to make a prediction on,
Yes.
that model is going to be a lot better than something you can build with 50 people. So that's the point of putting those things. So that middle question is getting answered. And how do we know the patients are real? That's the biggest question. So there's a demo on how to do this. There's a GitHub repository. And I need to update the documentation with more animations for the Shiny app. Yeah?
So what domains of the CDM are currently supported?
Pretty much everything but, everything that has structured data. So you can use devices, you can use procedures, you can use observations, conditions, drug exposures, and node NLP.
So what about visits? Sorry.
Hmm?
What about visits?
That's a tricky one. Yes. But, the code is there for it because somebody internally at Stanford built it in because they were stubborn that they wanted to do that. So the code is there, and the functionality is there. It's just not exposed to the people.
Why is physics tricky?
Well, because you know, in Odyssey, you only, well, at least up until a few months ago, you only had 4 types. So you could only have, you know, inpatient, outpatient, emergency room visit, and something else. So for us, for Stanford, we had to funnel 120 different visit types into 4. And by losing that resolution of the data, anything you built on that was bad.
This is one of the #1 complaints of ETL people.
Well, now there's like 15 though. Yeah, they added some more. But still, you know, funneling all that stuff made very bad models.
Even in that article, one of the criteria was that event that led to hospitalization or death.
Yes. So yeah, but I think they added more visit types, so now there's more. So maybe, I mean, so the functionality is built in there, and once, you know, that gets better, I mean, it could use visits. Yeah.
How do we add the cost table, payer plan period?
Oh, that's a good point. Yeah, I don't have anything for cost here because we had EHR data. So basically, you just have to add another section where you pull from that data, from that table. Yeah, it wouldn't be that hard. Yeah, but we should definitely talk about that because I'm interested in adding functionality, so that's definitely one good thing to add. Yeah?
Have you ever thought about trying to identify, not necessarily like the patient has this attribute, but like that something that was stopped and began this period of time, so that like basically like these series of drug exposures are one treatment regimen, and then this other series of drug exposures is another one.
Not yet. Yeah. So definitely, that's one of the things where this is going. That now we're able to tell you for, you know, the phenotype probability at some point because you feed the data at that point, right? But if we're working on something more smart to be able to do episodic or periods of time and predictions at multiple periods of time. So that's.
Like a cascade pattern, is that what you're asking? Yeah, so I'm like I want to label that like these 15 clinical events are like a treatment regimen, and then this next 15 are basically switch to a different treatment regimen.
Yeah, no, so now you can I mean, you can feed the data that way and it will do it properly, but there's no automated way of doing that as of now. Yeah. But if you feed it, you know, feed patient 1 from time 1 to end of time 1, and then feed patient 1 from time 2, end of time 2, then it will give you probabilities at different points.
So that I can find all the other, like when the treatments began then for other patients without having to manually review each one.
Yes, yeah.
And Juan, it sounds like Atlas is giving you much more of the temporal flexibility, right? Because
Yes.
you basically, it's yes or no.
Yeah, so at the end of the day, yes, it collapses. But, you know, I mean, all the functions, I mean, the low-level functions, you can feed the people in whatever time intervals you want. We just haven't provided an easy way of, you know, doing that. And that's where the research work that I'm doing in my lab now, it's going to. It's finding a way to defining or somewhat, you know, try to figure out how to do that, which is hard. Cool.
One last question.
Uh-huh.
Just so that I can visualize this very well. So once the model is trained, you have a model, and it's in a library, and somebody can take it and have a small data set and use it with data.
Uh-huh.
But the idea is that the model itself, knows based on the assumptions themselves what features matter, right?
Yes.
But then if those features are not available in that small data set, then is the model useful?
Well, yeah, that's a very good question, and it will depend on what features you have,
Okay.
right? So, I mean, but the top features must be stuff. It will
Some
usually
standard.
be stuff that's standard, yes.
Okay, so
And since
something
we're
to just think about, it's just like standard stuff.
Yes.
Okay, so then it's your responsibility to sort of look at your data and see whether you're
exactly, yeah. Because I mean, if I train this on SNOMED and then you try to run it on a place with ICD-9s, you're not gonna find anybody, right? I mean, it's not gonna be any useful. But with Odyssey, at least, you know, all the features are standard from the concept, right? So from the vocabulary. So at least, you know, if you map properly, you'll have stuff that matches.
Yeah, so you see, I think I know where I dropped my logic is forgetting that wherever you're transferring, it's going to be CDM data.
Mm-hmm.
Okay, and
Yes.
I need to stay with that.
Yeah, no, because the first iteration of this was non-CDM data, and nobody could use it because everybody had to convert data to a format. With this, I mean, anybody with a CDM, yes.
Okay, that's great, thank you.
Okay, so you can try it, and Joel's next. Thank you.